Welcome, Calculus AB. This is 4.3, Definite Integration. The essential question is, why didn't I teach this stuff last week, and what happened to Riemann sums? Let's begin. So, what's the definition of definite integration? We did this a little bit last week, but just to go over this again, is I have this notation right here with this elongated s. This is like the sum of the area. So, the way we say this is the function f of s is integral on the domain a to b. And a we call the lower limit, and that's why it's at the bottom. And b is called the upper limit, and that's why it's at the top. All right, just vocabulary. So some theorems behind all this where you can say that if f is continuous and the interval a to b is closed, then f is integral on a to b. And that means that the definite integral of f of x from a to b does exist. All right? And the definite integral is actually an area of a region. So that's what we kind of got into last week, but here it is again. The area of some region is the integral of f of x from a to b if f of x is what bounds it on the top. So let's show some pictures of this. So I want to write an expression for this area. So I have this function f of x right here, which is 4x minus x squared. And I want to write an expression to do all this pink area that I'm also coloring in right here. So I can write an expression for a definite integral right here. So it's going to be from, what are my distance? Well, this is 0, and this is going to 4. So it's from 0 to 4. 4 is my upper, 0 is my lower. And the function is 4x minus x squared and dx. So that's an expression. All right, and so you can evaluate an integral by sketching the region. So sometimes, like, we taught how to do the antiderivatives last week, but let's say I just want to sketch this region and not do it with antiderivatives. So I'm going to sketch the function of 4. So f of x equals 4. And if you don't remember what that is, 4 is just a horizontal line. So I'm going to go up 4 and draw a perfectly straight horizontal line. Let's make it red. So you can draw a line right here. And so in your bounds, your upper and lower at 1 and 3. So 1 I'm going to put here, 2, 3. So 1, 2, 3. And this is at 4. So I'm going from this spot right here. Actually, let's make it a dotted line. So I'm going from this area right here to this area right here. And I want to find the area of this region. We look at the shape of this region and it looks like a rectangle. And you know your area of a rectangle equals the base times the height. So in this case, your base is going to be how many units? Well, you're moving over 2 units, and your height is going up 4. So the area is actually 8. Now, what's kind of cool, I'm just going to show it to you. We can go do our integration and antiderivatives we did last week. So 4 is going to be 4x from 3 to 1. And if you plugged in 3, you get 4 times 3 minus 4 times 1, which would be 12 minus 4, which would be 8. So I get the same area either way. Just showing that, hey, you can actually sometimes create a shape, and if you know the area of the shape, you could solve that way. Let's try another shape right here. So I'm gonna graph this function of my f of x equals x plus 2. So that's going to be a line, and that line is going to be starting from up 2 is my x-intercept or y-intercept, and the slope is up 1 over 1. So I'm going to just draw a rough sketch like there. And my bounds are going from 0 to 1, 2, and 3. And if you know it goes up 1 over 1, so this is going to be at 3, up 1 over 1 at 4, it's going to be like right here. And that means that 5, which we're not to scale here, but don't fault me for that, it's going to be up here. So I'm drawing a sketch from this being my 3 to 0 right here. So I'm sketching this whole area. You're like, well, what kind of shape are we drawing right here? If I want to go by shapes, this is a trapezoid. These are 2 parallel sides, and so we have a shape of a trapezoid here. So we could do the formula for trapezoid is b1 plus b2, the average of the bases, so divided by 2, times the height. So in this case, base 1 is going to be 2, base 2 is going to be 5. So you have 5 plus 2 over 2, times the height, which is going to be, this is your height right here, is going to be 3. So it's going to be 7 halves times 3, which will be 21 halves, or 10.5. Cool. All right, I can do another one. This is actually, if this, my f of x equals the square root of 4 minus x squared. If you know this is the function for half a circle. You're going to have a half circle shape, and that's a circle, looking like this. It's going to go from 4 to negative 4. So I want to find the area of this. So to find the area of this, but I only want to find the whole area. Actually, it's not 4 to 4. excuse me, it's going to be from negative 2 to positive 2. That's the radius. The radius of the circle is 2 when there's a 4 there. So the formula for a circle is the area of a circle is going to be pi r squared, but in this case we want half of a circle. So the area for half in this case is going to be 1/2 times pi r squared. And if my r is going to be 2, it's 1/2 times pi times 2 squared, which will be 4. 4 divided by 2 is 2, so your area is going to be 2 pi. All right, so some properties of integrals, I might have mentioned last week, if you're integrating and your lower and upper bounds are the same number, a, whatever the function is, your answer is 0 because there's no area there if one of the sides is 0. Also, this other property, if you integrate from b to a, that's going to be equivalent from integrating from negative a to b. So what this means, if you swap the a to the bottom and the b to the top, you're going to have an opposite. It's going to be the opposite. So if the integral from a to b was 5 here, this would be negative 5 over here. All right, so let's evaluate some integrals. So for the first one, hey, it's sine of x, but we're going from pi to pi, we know that's going to be 0. The second one here, well, it's from 3 to 0, and that's kind of weird. We can rewrite that as negative. Just do the opposite from 0 to 3. Put the larger number on top from x plus 2. And if we used our old system, this would be x squared over 2 plus 2x. We'll negative all that from 3 to 0. And you'll plug in negative 3 squared over 2 plus 6. And that'll be minus 0 because that'll just evaluate to 0. So what you'll get for your answer is 9 over 2 plus 6. So 9 over 2 plus 6, 9 over 2 plus 12 over 2. And a negative of that is going to be negative 21 halves as your answer. Hope you could see that. You can break up definite integrals into parts. So we have a picture of a graph. I'm going to change the view on this. This is way too hard to see. Entire page. Sure, yay. Okay, so you can break up a definite integral into parts. So I have this graph right here. And this is some curve, we're going to call it f. And we're going from a to b. And then there's some point c here. Well, I can break that up into different chunks. So I can say the whole integration is equal to the sum of the parts. This is similar to like the whole line is equal to the sum of the parts. And this theorem kind of illustrates this. From a to b is the same thing as from a to c plus from c to b. So I'm breaking it up. And one case where this is really useful is when you're talking absolute value. So the absolute value function, absolute value of x from negative 1 to 1. If you don't remember, absolute value looks like a v. Basically, you're taking the line of f of x, but whenever it would have going to be positive or negative, make it positive. So we're going from negative 1 to positive 1. We have to actually break this up into chunks when using absolute values. So I got to find the area of this plus the area of this. Well, this is equivalent from saying from 0 to 1 of x plus from, it'll be from, well, so think about it this way. If this was the regular x function, we would be going down right here, and this area would have been negative. So what I can do instead is say you're going to be adding, I can think of it as subtracting that negative area. So I'm going to think of subtracting the area from negative 1 to 0 of x dx. So this would have been negative area normal, but we want to subtract it to make it positive area for that chunk. So if I evaluated both these, this is x squared over 2 from 1 to 0 minus x squared over 2 from negative 1 to 0. All right, and evaluating all this work, you'll get 1 squared over 2 minus 0, and minus, it'll be 0 minus negative 1 squared over 2. And what happens in this case is this negative, negative 1 squared is 1, negative makes it positive, so that'll equal 1/2 plus 1/2, which equals 1. All right, that's it.